public. He has also published several scientific research papers in the leading peer-reviewed journal in his area. Now I would like to invite Dr. Anupam Priyadarshi to enlighten us with his talk on Introduction to Mathematical Ecology and Role of Differential Equation. Welcome you, sir.
Thank you. Thank you, Pooja. So, a very good afternoon, everyone. Uh, I'm very grateful to my senior Joginder sir. He was my senior at BHU when I was in MSc, and he was doing a PhD at that time. And the bond between us was quite good. And 5 minutes earlier, I was talking to him about this, that becoming a professor in BHU and be a student in BHU are quite different things, right? So BHU is we can heaven for the students, but for the teacher, the same thing may not be true. Anyway, so that's what we felt in Banaras Hindu University. And let me correct one thing, that I am not an associate professor. I am just an assistant professor. Have joined in 2016, and I was at the scientist post at various institute like Nimbayas. It is one of the leading institute in mathematical biology. We call it the National Institute of Mathematical Biology and Synthesis, and it is under the University of Knoxville, in University of Tennessee, Knoxville in USA. And similarly, I had worked with the Blastimil Krivan, and then I moved to the Tokyo University where I worked with the oceanographer, where Professor Yamazaki Sensei was my supervisor. So these are the things, and currently we have working in something like a very different type of ecology. We call it closer modeling approach, and we published in a Nature. And you might go through the Google and you will find out that there is a paper in Nature in which I was the leading author. Anyway, so today I am very glad to have this yeah, this this workshop. Actually, Joginder sir has talked to me about this because at the same name we have already performed the last year the same workshop with Dr. Ravi Pratap Gupta here in BHU, and the experience was quite good. So I just tell Joginder sir that go ahead with this, and there are various talks on this topic which is needed to extend it. So if you were present in the last lecture, which was delivered by K.S. Mathur, then I think you may understand that how differential equations have been used to to model anything, model at least the ecosystem pattern or ecosystem events. Someone is
Did
getting
the mic
noise.
on?
Yeah, someone is getting. Please mute it.
Participants are requested, please keep their mic off.
Okay, so
Thank
so I hope that the slides are visible to you. Yes, slides are visual.
Yes, sir. Visible.
Okay. So the topic is Introduction to Mathematical Ecology or Biology and Role of Differential Equations. So seeing a differential equations, we always think about to solve it, isn't it? Because being a mathematician, you always try to see the differential equation and get the auxiliary equation, then general solution, and so on, right? And lastly, you will finally will be very happy to have the analytical solutions. But these are the things for the linear things. When you have a linear differential equations, you might be get the using the superposition principle to get the analytical solutions. But the same thing does not apply when it becomes a non-linear differential equations. And one of the most leading topic in physics is going on, that is the nonlinear dynamical systems. And using the nonlinear dynamical systems, the concepts of nonlinear dynamical system and their applicable tools, we use in ecology as well to find out the patterns. And why it is so? Because we want to know that how ecological process happening is happening, and how it will happen in the future, and how it will go ahead. That means the same pattern of ecology will resume or will remain constant throughout the time, or it will change. And the future cannot be done by experiment. It must be done by theory. So if you are doing the experiment, then you go through the theory and then develop based on the theoretical concepts or theoretical results, you will develop the future predictions of any ecological pattern or events. So basically, we are interested in the following research. It might be possible that we are interested in individual ecology or the community ecology. So when I say plankton, that means I am working with the whole group of the plankton. That means phytoplankton, zooplankton, diatoms, and so on, right? Similarly, if I tell you about the rats, that means I am talking about the bigger rat, the smaller rat, the length of the rats, and the strong rat and the weak rat, and so on. That means I am not differentiating at the individual level. So I'm talking about at the community level, how the whole community will work. So it's look like simply that not going through the individual, but going through the community presence or community impact on the ecosystems. So uh, if we are talking about the community ecology in the ecosystem, we have mainly three types of the interactions, isn't it? So if you have, let's say, X one species and Y one species, it is only possible that they are competing each other for their survival, for the same resource of the food or light or water or so on, right? So for their survival, they are competing each other. And in that case, both are at the disadvantage positions, right? Or it might be possible that they are together mutualism, and both are benefited, right? And it might be possible that one is at the advantage level and another is at the disadvantage level, isn't it? So one is just predates on other, and it will comes out to be a predator prey functional responses or interactions, or we can say predations. So mainly three type of interactions in ecology are observed: competition, mutualism, and predations. You can combine each other, and you might be develop another one, but generally three type of these things are recognized in ecology. And if you recognize the three interactions, then what will be the tools to model it? The basic modeling tools is ordinary differential equations. It might be possible that you can use the partial differential equations. So you can say the differential equations. And in such cases, most of the cases, you cannot deal with the linear differential equations. You cannot say that I am going from this mathematics department of Banaras in the university to the Lanka gate, but in a linear fashions. It not be possible, isn't it? So, so it all the time modeling needs the non-linear differential equations, and basically we are generally we are dealing with the autonomous system. So, what is the autonomous system? When your ordinary differential equations or system of ODE has has not explicitly the independent variables in the right hand side. So suppose dx by dt equal to fx or fxy, right? But if I include t in a function, right hand side function fxyt, then it becomes the non-autonomous system. And if it is not explicitly included in the right hand side functions, then these type of called the autonomous system. Basically, in ecology or the ecosystem, you will observe that most of the, not the all, but most of the ecological phenomena can be modeled using just the autonomous system, right? And once you have, then what are the factors, what are the biological factors which which shape or which regulate our system? Two or three things are very usual or very in a general phenomena, like functional responses. So functional responses gives you how the predate prey is being predated by predators. So at which rate it is going to be predated, right? And opposite of this is called the numerical response. And numerical response will show you that how the predators convert these predations in their growth. So if they are taking, is the whole prey converting in their growth, or using the using the role of this whole predations in growth of the predator? That will cause you the numerical response. Most of the models assuming that the functional response and the numerical response are the same, are equal. But it is not the case, as we all know that we are eating too much, but in that proportions, our body is not responding in that much. So our growth is not so much, right? At the same level, you can think about the community. So one community predates lots of prey, but it might not be possible that the growth of that community will be so much faster with that predation rates. So that's why numerical responses and functional responses sometimes are not equal, and that is what realistic. So a good model must be simple enough to be mathematical tractable, but complex enough to represent the system realistically. And that's what this mathematical ecology lacks sometimes, and most of the time it lacks. That becoming a, I mean, modeling or model, system model, you cannot gives you the real systems, right? Anyway, so once you have a model, then you will try to find out the persistence and extinction of the species, the whole species. So if you have a model of two or three, then are these persist? That means with time continue, so infinite times, that leads the system at the persistent level or not? Or is there some species is going to extinction? And that's what we are investigating. We are searching for that using the mathematical modeling tools. And then how its parameter dependency showing with the system developed by ecology. So let's say how the growth term of the predator uh, of the prey is influencing the whole system dynamics. That's what parameter dependency is. And then we have nonlinear dynamical system tools. We call it a stability analysis, then bifurcation theory, and then chaos. So stability analysis means if we have some equilibrium point, that means the point where solution may not change, right, with the time. Then at that point, nearby that point, in the neighborhood of that point, if I start my solutions, the solutions may going towards that equilibrium point or may far away from that equilibrium point. If it is going towards, then it is a stable equilibrium point, and if it is going away, it is in a stable equilibrium point. But we have a very solid, or you can say developed, mathematical theory about this stability analysis. And then similarly, bifurcation theory is that how one system stability depends on the parameter change. So let's say if I have one system with parameter p, and that p nearby that p or p0, if system stability changes from stability to unstability, then the point is called bifurcation point, and we can say that the system undergo with the bifurcations. these are the basic things in mathematical ecology. First of all, as you can see here, the consumer and resources. So how many, one, this resource का मतलब है resource, that means we have the bottom trophic level. So it's on the bottom one. So it's just assuming the whole environment capacity and so on. So it totally depends on the environment and capacity. So it's called at the bottom level trophic level. And then the first trophic level is called the consumer. Whenever I say the trophic level, that means I'm assuming at that trophic level, every consumer, the growth of the every consumer depends only on the resource. That means the bottom trophic level and so on. You can change it. So this one is called the food chain because from this resources, energy is going to be the consumer, and consumer whole growth depends on the resources availability, right? Similarly, if you have a tritrophic food, such a system is called ditrophic food chain. And if I increase the chain, let's say one more or higher trophic level, we call it the predator. So let's say resource, consumer, and predator, the energy will flow from the resource to consumer. So consumer growth is totally depending on the resources in absence of the predator. And similarly, predator growth rate is totally depending on the consumer availability. But the consumer now becomes the prey for this predator. So now the consumer has the implicit effect of the presence of the predator. So whatever the growth of the consumer was initially with only depending on the resource availability, now the growth totally responsible with not only the resource availability but the presence of the predator, or you can say the predator risk, right? So how the predator imposes the predation risk to the consumer will decide how much and at which rate consumer growth will be developed. So these are the very simple ditrophic and tritrophic food chain, and you will be amazed that the dynamics of these things, this resource and consumer, might be the point of stability or might be the oscillations. So the best example I will show you very quickly is the Lotka-Volterra model, in which the one is prey and another is ditrophic food chain, and then it will see that how the neutral oscillations will come out. But as you increase from ditrophic to tritrophic, that means from two trophic level to three trophic level, the whole dynamics will change, and you will understand how it will change. So suppose it's a very simple things to understand it without any mathematical equations. That let's say this is the phase plane. Phase planes means you have a prey on the x-axis or predator on the y-axis, and it might be changed. It doesn't matter much. So let's say prey and predator phase plane here. So what will be the most maximum dynamics here? So it will something like if you start from the solution here, it will go to the here, and if you start from here, it might be oscillate like this, right? So there is the limit cycle or the point of stability. But think about the three-dimensional things. Once you are thinking about the three-dimensional, let's say this one. So you have a prey, and this is predator, and this is the higher predator. So this is a three-dimensional. The now if I have my equilibrium points here, so it might be possible that the oscillations is not only at the plane, but it is in the three dimensions. And at the similar way, this three-dimensional limit cycle is not the same as the two-dimensional limit cycle, right? It might be possible that you can project the three-dimensional limit cycle to the plane, but the one axis will gone, right? And this will leads if I have a lots of aperiodic limit cycle where period cannot define with the definite point, then it will leads to us the chaos in ecology, and that's what I had just escaped in the last slides here. Chaos in ecology. So chaos might be possible, and in three dimensions, not below to the that, and it is only for the continuous autonomous system. Similarly, you can just see here, this is the one resource and consumer and predator, where you have a food chain now. These are the examples of the food waves now. What happen if I increase my chain? Uh, it might lose the stability, or it might gain the more stability. There are two different type of ideas developed parallel to each other. Some of them find out that increasing the chain might lose the stability, and some of them find that increasing the length you increases the stability of the whole systems. So I'm not going to go with this debate, but you must understand that increasing the chain, it will lead to the mathematically intractable, in the sense that you cannot have the command of each of the species, right? So these are the very simple things. One can play with it. One can develop the mathematical modeling, as you can see here. And just I put the predator some ordinary differential equations and consumer for some ordinary differential equation and resources. You will get a system of differential equations, and then you will solve it. Analytical solutions will not possible, so you will go through the some of the qualitative analysis, and the qualitative analysis I think uh, will be discussed tomorrow, so I will not go through much. So what is mathematical modeling? I think Mathur has discussed a lot, but let me tell you one story about this. So mathematical modeling is nothing. It is the formulation in mathematical terms of the assumptions believed to underlie a particular real world problem. Once I tell you about the particular real world problem, uh, with the simplifications to develop mathematical modeling, the real world problem may not be gives you the real solutions, and that's why sometimes modeling is not very encourages in such a different situations. Anyway, so suppose you have a bacterial growth in your laboratory. So in one flask you have some sugar, and then you have two bacteria or one bacteria, and in another flask, sorry, after some time, or 1 hour, not 1 hour, but 2 or 3 minutes, you will see that it becomes a twice, it becomes might be a thrice, and so on, right? So bacterial growth is generally assume exponential growth, right? But what it will tell us? It will tell us that the growth of the bacteria with the time is totally proportional to the presence of the bacterial populations at that time. So dn by dt is nothing, but it is proportional to the n, the initial population in the flask. And this is the k is the constant. So what will be the solutions of this? The solutions is a depends on the, of course, initial populations and exponential kt. So as you can see here, whatever the, if you find out it is a constant, then nt is just proportional to the exponential one, and so it's going to be exponential growth. But this type of modeling is not in realistic. In real system, after some time, the whole bacteria will die out, isn't it? Because it's totally dependent on the sugar available in the flask. Anyway, so why modeling is necessary? Because explosion in biological research and progress, and then it is the fundamental quality way to understand and analyze complex systems and phenomena, and it is a complement to theory and experiments and often integrate them. Uh, where the experiments fail, the theory will come out, and then modeling will help to understand again the correct experiments of that type of theory. So theory and experiments integrate together. So anyway, becoming widespread in computational physics, chemistry, mechanics, materials, biology, and mathematical sciences will be an integral part of this modeling. So people will always use the quotations that few mathematical scientists are biologically educated, but few biological scientists are mathematically educated. And if both are working together, that will be a good problem solving challenge or opportunity. So basically, mathematical modeling deals with the three different branches of the science: computer science, mathematics, and sciences. Science, that means involves everything: biology, biochemistry, biotechnology, and so on. And it will deals modeling will deals with three things: the experiment, theory, and computation. So computations, it might be possible that with the experiments, you will use the theory, or you will develop a model, and that with that model you will compute it, and then computations will again verify the whole experiment, and then again you will have the theory development and future predictions and so on. So nowadays, mathematical modeling are uses in various branches of science, as we sometimes say that every branch of science must use the mathematical modeling. Anyway, so it's a very wide statements, but still it is a very effective one. But the first example I have chosen for you is the first jetliner, and which is to be digitally designed. So assume that if you are if you are in an industry where you have to propose the jetliner. So you pre-assemble all those uh, one time, two times, three times, and all those are failed. Then 100 times you will failed. But imagine the same jetliner in a digitally design or pre-assemble on your computer. You will use it. You will do the whole thing 100 times, 1,000 times, and so on, and it will gives you the correct one, right? So how this mathematical modeling has developed or helped the industry to develop all those unrealistic things in a real world. Similarly, how we think about the human brain. You cannot go through the human brain, each time of human brain, and do the MRI and so on. So the MRI will give you the facility to understand how the brain will work, and how the brain is working, right? Similarly, on the climate modeling, you have the predictions of the tomorrow, Tuesday, sorry, next day, tomorrow, and so on. It might be possible that you have a climate predictions for a month, and it is only possible due to the Lorentz model, right? So thanks to the Lorentz, Professor Lawrence, who had understand that why mathematical modeling uh, is needed for the climate modeling. So if you have a mathematical modeling, then these are the very simple process way to do this. You choose the real world problem, you simplify it in your own words, and then you develop the working model. Once you develop a working model, you represent it in the mathematical modeling by using the differential equations, either ordinary differential equations or partial differential equations, then translate it in a computational way. That means you are estimating the parameters and so on. Once you have the parameters and all those mathematical modeling compartments, you will simulate it. And those simulations will give you the results and conclusion. And those results and conclusion must interpret it with the real world problem which you have already chosen, right? Once you have chosen, then you can predict the future of this real world problems, right? So a very simple example, that is the, if I ask you that how do things get moved around inside cells? I mean, it will be very difficult for a simple scientist if they are not using the mathematical modeling, because it needs a lots of hard work to do the experiment and to get each of these things, right? So a simple way is to cut it, transactional cut it, the sale, and find out that how the retrograde motor to anti-retrograde motor move inside the cells, and that's what we are doing. So the excellent paper for axonal transport is written by Brown in 2000, which was in Nature Reviews, and it is excellent one. to understand without much mathematical point. So you will understand without any mathematical things. So it's a very excellent paper. And then the mathematical ecology is totally dealing with the population ecology, and it all started with the data we have for a uh, rabbit or hare, a snow say hare, and lynx. So Canadian lynx look like a cat. It's between the, you can say, tiger and the small and the pet cat. So it's between these two, and so it's look like a cat. And the whole Canadian lynx depends on the how it predates on hare. That means the rabbits or rodents or a small prey, right? So the data has been collected from 1900 something like 1835 to 1934, and the data was like this. So as you can see here, the bigger pics, which is the halo circle, is representing the rabbit. This one, the prey, and the lynx, that is the Canadian lynx, represented by the filled circle. And you can see that these filled circle are below to the peak of this snow shade rabbit. Anyway, so looking with this only data of both the data at one phase, how you will predict that it is a prey-predator model? A very simple things to understand that is it in real the prey-predator system or not. So here where you have a data and you are not supposed to, or you are not giving, or you are supposed to give some reason that this data represents only the prey-predator model, you need the theory of prey-predator model, and that's where the mathematics play a vital role. That's where the mathematical ecology helps you to understand the ecology with a very basic data, right? So what happening actually, that in pre-predator cycle, we knew from the mathematical point of view, without any data, we knew that pre prey pig comes first, and then it will comes out with the predator pigs. So look at the pigs of each one. Look at the pigs of prey, each one, right? Right. Then you will see that the predator pig follow after appearing the prey, right? And this is what we call it the concepts of the prey predator model. That is what the general framework of the prey predator model is, without any mathematics. I mean, uh, you can use any mathematics, but without any mathematics, the concepts or the framework of the prey predator model is that the predator's peaks must lags behind from the peak of the prey peak, and that's what pre-predator model is. So looking for that in a simple mathematical modeling, you can estimate the whole parameters of prey and predator, and then one of those model has been developed with this data. The data has been taken from the previous one, and as you can see here, the same thing is happening, that the prey peaks come first, then predator peaks, the prey peaks come first, come first. That means predator peaks lags behind the prey peak, and that's what the prey predator model is. It does not matter what parameters I am choosing, what this concentration is choosing, what population of prey is choosing. It doesn't matter. You choose the 700, you choose the 7,000, and so on. It does not matter anything. It will always lag. The predator sticks always lag from the prey picks, and that's what. How how will understand this? Those who are not very interested in complex system or complex development of the mathematical modeling, I will strongly suggest to go through the net logo. Net logo is developed by one mathematical biologist from the European countries, and uh, he has, Yuri Benkley has developed this one, and freely develop, distributed to all the world. So just go through it. If I have a time, then I will show you that how you will understand the net logo in a very easy way. Anyway, so I think time will not permit me to do this. Yeah. So just go through it, and once you have a problem, write to me. I will help you in every possible way. Now, so how do predators respond to prey? Well, already I have discussed about the numerical response, functional response, and development response. How the predator growth depends on numerical responses and functional responses. But we have very much thankful to this man, the Professor C.S. Holing. And why we are so much thankful to him? Because before him, the people are generally using the exponential growth, which is not true. So he suggested that the feeding rate of predator is not independently or not totally the depending on the carrying capacity or environment capacity. It might be a possible it might be a function of prey density. So that's why the whole mathematical ecology world is very much gratitude towards the Professor C.S. Holing, sir. Anyway, so let's look at the basic predator prey model. So basic prey predator model, that means I'm talking about the N as a prey and P as a predator, and we will have the equation. So let's start with the N. So if I have dn by dt, as you can see here, n is here, so you can change here. Anyway, so it represent the left hand side represent the growth rate of prey per capita. That means how one individual prey is growing. So it's growing with the Rn once the sorry yeah sorry, this is the minus one, so please correct it anyway. So if it is absent from if the predator is not present, so in the absence of predator, the prey growth per capita is nothing but as a constant, let's say Rm. Similarly, similarly, dp by dt, the predator growth per capita is nothing but it is the same thing. That means the numerical response, how it predates here. So it's going towards the energy transforms of the prey to predator here, and the natural growth rate. So this small r represent the intrinsic growth rate. That means it have all birth rate and the death rate of prey in absence of predator, and this one is the natural mortality or death rate of the predator. Right. So uh, how will look at the solution of this type of system of differential equations? One of the easiest way to do is just dp by p dt equal to 0. So equating each differential equations equal to 0 will give me that at that point, at least at that point, the prey or predator does not grow or decay. So let's do the same things. So here, so the whole equation is computed or compared with the 0, and we will find out that capital N, that is the prey population, is nothing but mu by Ca. Similarly, predator population is nothing but it is R by A. So whenever N equal to mu by Ca and P equal to R by A, N equal to mu by Ca, the predator does not grow or decay. Similarly, P equal to Ra, at that line, the prey population does not decay or grow, right? So using the same things. Let's have this n and p. So n equal to mu by Ca. There is a red line at which predator growth neither decay nor grow, right? Similarly, the blue line shows that dn by dt that equal to p by ra, p equal to r by a, and at that line the prey grow does not decay or grow. So let's start with our solutions from one point. So let's say here. So what will happen? At this line, this is the point, this is the initial point where pre-growth does not decay or grow. So there is nothing change in prey. So only predator will change. So where it goes, right? The question is where it goes. So this line will show you that the predator increases in that line because there are lots of prey here. You see here, this is lots of prey here. So due to the availability, too much availability of prey, predators growing in the right directions. And then you will find out that it will go again here. So now the solutions comes here. So what will happen here? Here there is no point where, I mean, either prey grow or predator grow. So since the availability of predator is too much, I mean too high, so a predator again going towards in the right directions, but since predator has the high populations, and henceforth the prey population decreases due to the predations. And then if you know the vector analysis, then the resultant will be in these directions. So you have next point of the solutions in here, and at that point what will happen? Dp by dt equal to 0. That means the predator does not grow or decay, and henceforth only prey will go on decay. So the prey is still decaying because the presence of the higher number of predator populations. And so you have another point, and then do the same things. You will get it like this, right? So choose at any point, you will find out your whole dynamics. So what will happen? I have started from this point, and then my solutions is going out like this. So most probably I am expecting a oscillations here, and that's what we are expecting here. So what will happen? It will just oscillate from the same point and come back to the same points, right? So what happen if I increases too much prey? So nothing, but it will again doing the same things and coming back to the point, right? And what happen if I have a very low point of this? Then it will comes out to be this, right? And this point, the intersection between the red line to blue line is called equilibrium point, where neither prey nor predator grow or decay. And this is what the neutral stability is. This is what Lotka-Volterra has proposed, and we can have this as 1 2 3 4, and you can see that the phase line of this 1 2 3 4 is represented by the same here. And you will see that the lack of the lack of this one, the phase, the peak of the peak lacking behind by 1 by 4 phases. And this is what generally we have links, snow shade here and links. So I think we might go through lots of things, but I think time will not permit us to do this. So if you are looking for a logistic growth or some type of differential equations to use your data, I will suggest you to go through the logistic models, and I have shown you for the logistic model here, a very simple one. So this is the logistic model, right? dp by 1 by p dt equal to k into 1 minus p by k, and I mean the whole explanation is here, but let me show you that how it will use. So I mean, these can be, you can just read it and find it out. But how you can use this one in your real world problems? So one of the most simplest way to find out the real world problems is here, right? So here dp by d equal to r into p into 1 minus p by k, and if you are equality equal to 0, it will gives you with r equal to 0.0 and k equal to 400, p equal to 0 and p equal to 400. So one can just solve it, and you will see that p equal to 0 is just source and p equal to 400 is a sink. You can see here, right? And you can see here. So it is a source. Source, that means you will start nearby the solutions, it's go away. And sink, that means if you start from nearby positions of that p equal to 400, it will comes out to be approaching the 400, right? Similarly, if I so imagine you are in a pond and you wanted to harvest some particular fish, right? So you just model it by your just logistic model. So I have a p as a particular fish, let's say trout, and then I have a growth of this, and then I harvest with the h. So I harvest with the constant rate 3 by 4. Once I harvesting this 3 by 4 with the same r equal to 0.01 and k equal to 400, you will see that the now the source and sink has been changed. So now p equal to 100 will become a source and p equal to 300 become a sink. Here you can see here, this is the sink one and this is the source one, right? But what happen if I increase my harvesting? So suppose I harvest at the rate of 10. So what happened? Well, just solve it. So just putting the r equal to 0.01, k equal to 410, p equals comes out to be 200 plus minus of 600i, right? So there are no solution. That means the all fish die out. You cannot have the higher harvesting. So how much I will harvest it? That's the question. And to find out, that's the question, mathematics will help you. And it will say that p equal to 200, 1 plus minus square root of 1 minus capital H. Now you can understand that 1 minus capital H, that means H must be less than 1, right? To have this real solutions, to have a fish coexistence. And here I have shown you that if h is less than 1, then we have a two two solutions, p1 and p2, that is a source and sink, right? As you can see here, so x-axis is h, capital H, and this one is the equilibrium points of p, so this is the capital P. So you have a P1 and P2 when you have H is less than 1. So here and here. So one is the darker line is showing you the stable one, and this dotted line is showing you the unstability. So we have for h equal to 0.5, we have two solutions. One is the stable one, another is the unstable one. One is the stable one. So h is less than 1, you will see the harvesting will gives you a stability or unstability depending on how I choose the initial value of s is there. So how the initial value of s is there will decide us that it is the sink or source, right? So what happen if h is equal to 1? So what happened at h equal to 1? As you can see that the both the solutions come to converge at that point, and after h is equal to 1, there is no solutions, right? So that means this is the critical point. This is the bifurcation point where, or I mean below this, you might have a stability or de-stability, but after that you cannot have the phase existence. So the phase extinct. So this is all, if h is greater than 1 happening, then it will comes out. So this is how the qualitative behavior of any ecological pattern will be done by using the mathematical tools, a very simple way, man. So if you have any problem, I mean, I have put it a lots of for biological students, a lots of experiments and data. But if you have any problem, let me know. So thank you so much, sir.
Yes, yes. Thank you very much, Dr. Anupam. Very first, let us take question from the participant if there is any question. Participant, you may raise your hands if there is any queries from your side. Then we will call you one by one. Yes. So we have one question from Shruti. Yes, Shruti.
हेलो सर सर आपने अभी एक
Yeah.
स्लाइड शेयर करी थी विद रिस्पेक्ट टू हार्वेस्टिंग यू आर चूजिंग
Mhm.
द वैल्यूज ऑफ स्मॉल आर एंड कैपिटल एच विद रिस्पेक्ट टू पर्टिकुलर वैल्यू तो
Right.
हाउ कैन वी चूज दिस वैल्यूज
Oh, that will lead to the parameter estimations. You must understand the parameter estimations to do this. So all those parameters involved in a mathematical or ecological modeling, you need parameter estimations,
okay this is
right?
just a parameter estimation we can use a particular range for these parameters also
Of course, of course. The range of the parameters are available in the literature, or you can go through the, experimental works and laboratory works, and that will help you to get it.
okay thank you sir
Yeah. Is there any more question from the participant? Okay. Then I will invite Pooja ma'am.
Thank you, sir, for your very informative session. I'm sure this lecture will definitely help us to understand mathematical ecology, modeling, and role of differential equations. I hope the first day of this FGP was very informative and benefited to us. Now, tomorrow the session will be started at 10 a.m. and thanks for joining us.
Thank you, everyone.
Thank you,
If you
sir.
Yeah.
have any problem, write to me directly. It doesn't matter.
Definitely, sir. Definitely, sir.
Uh, can we have pics? If participant can on their video, we may have some pics for our record. Yes. Everybody. Very good. पिक ले लीजिए एक मिनट
Okay.
ले लीजिए हो गया हम्म? तो
Okay. Thank you,
Okay, then
everyone.
thank you very much, Dr.
Thank you.
Anupam, for your wonderful
Thank you,
talk.
sir. Sir, thank
I
you.
believe
It's a
that
very informative
participants will
session.
be benefited with your talk. In the end, I see there is one participant might be he has some queries. Yes, Mr. Uh, Lalu, I'm sorry if I'm not. Yes, you can ask.
Yes, sir. I'm Mr. Lakhan.
Okay, Lakan. Yeah.
Sir, in a competition model, a limited carrying capacity, what is limited carrying capacity?
See, if you if you are using uh, the environment as a free from any limiting things, then anything will go ahead, and the competition will not give you. There were no competitions at all, right? If I if nearby my house I have a lots of or several shops, then why I'm going to in a queue? No, I'm not going to queue. But if only one shop is open and there are 100 customers, then I must be in the queue, isn't it? So competitions comes when resources are limited, and that's what the concepts of these simple things converted in a competition model of mathematical ecology.
Yes, there is one more person.
Okay, sir.
You can ask your question. Yes, who is this? 5054.
Yes, sir. And sir, in any mathematical model, use a functional responses. So, how is a model a good? Any functional responses, calling type 1, 2, 3.
Right. It depends on the data. It depends on their behavior. So, a simple example you can see here that if there is a predator and there are two or three type of prey available. I mean, two, three types. That means different communities of the preys are available. So, what it happens? The predator has only one guard, right? So once I have eaten something, then for some time I'm not going to eat for the other prey, isn't it? So depending on such a situations where I am using the predator or prey functional responses or any functional responses, the things will comes out with the data. And Professor Holding, C.S. Holding in 1959 has done the same thing. He experimented with different type of a species, and he will find out, we call it a disk model. We find out that okay, some predator prefer to predates in a constant rate, that is called Holding type 1. Some predator behaves that he predates more and more when prey availability is more, and very less, or you can say the less predation rate when the prey availability is very low, right? And some other are doing the same thing. So we have S type of sigmoidal polling type, and we have Holding type function responses and so on. So depending on the data, depending on the predator's behavior, depending on the traits between the prey and predator, we have a functional responses. So you must go through the, I mean, CS Holding type of functional responses for a basics one.
Okay, thank you, sir.
Okay, thank you, Dr. Anupam.
Thank you, sir.
Thank you very much
All
for
right, sir.
accepting
Thank you.
our invitations.
Thank you so
And
much.
I hope that we will continue this collaboration in future
Sure,
as well.
sure, yes, sir.
And thank you, all the participants, for joining us. Tomorrow we have great speakers like Professor Piyush Chandra and Professor P.S. Datti from TIFR Bangalore. So let us join together tomorrow. Thanks all. Thank you very much, everybody.